Hey everyone, we're going to take a look at number 8 in section 3.10. Lots of words here. Um, we have a road that's perpendicular to a highway uh, that leads to a farmhouse located A equal 1.5 kilometers away. Now, your value of A could vary, but it should be some number of kilometers away. So you have the house that far from this highway. You have an automobile that travels past the farmhouse at a speed of V equal 81 kilometers per hour. Again, this number could be slightly different for your problem. So the automobile is on the highway. How fast is the distance between the automobile and the farmhouse increasing when the automobile is 3.7 kilometers? And again, that number may be different on yours. 3.7 kilometers past the intersection of the highway and the road. Okay. Now they do have a diagram in there, and we'll take a look at it. It's a lot of stuff going on there. So they do give you some variables. They want L to denote the distance between the automobile and the farmhouse, and S denote the distance past the intersection of the highway and the road. So the distance from the car to that intersection. So basically we have a house and it was 1.5 kilometers perpendicular distance to a highway. So here's my highway. This line right here is the highway. And so there's the intersection. If you come down, maybe there's a road perpendicular to the highway from the house, intersects the highway at this point. And the automobile was on this highway. Okay, the highway runs left to right on the paper here, and the automobile has passed the house, so it's somewhere over here now, and it's continuing to go to the right at 81 kilometers per hour. So they said let L denote the distance between the automobile and the farmhouse. So here's the farmhouse. Here's the automobile, calling that dashed line distance L. And then let S denote the distance past the intersection of the highway and the road. So the intersection of the highway and the road to the automobile, that's that distance S. Okay. And so you can see, because the distance here we're talking about is the perpendicular distance to this highway. This is a 90-degree angle, and you see we have a right triangle. That'll be important in the problem. So what information are we given? Well, we're told that the automobile is traveling at 81 kilometers per hour. And so notice that is the rate of change of S. S is the distance from the intersection to the automobile. S is getting bigger, right? That distance is increasing as the automobile moves to the right. And so ds dt is what's given. That is 81 kilometers per hour. It's positive again because S is increasing. And we're asked to what? Find how fast the distance between the automobile and the farmhouse is increasing. So that's L, right? That's the rate of change of L, dl dt. And we're to find it the instant the automobile is 3.7 kilometers past the intersection. So that will be when S is 3.7 kilometers. Okay. So what's the equation that relates our variables S and L together? Well, it's the Pythagorean theorem, isn't it? We have the sum of the squares of the two sides of this right triangle equals the square of the hypotenuse. Hypotenuse length is L in this case. So I have S squared plus 1.5 squared equals L squared. So 1.5 squared is 2.25. So that's now the equation that relates our variables of interest. We want to get our related rates equation. The way we do that is we take the derivative with respect to time. So let's put things in motion, right? This is a static picture. At any point in time, this relationship holds, right? Then we have this right triangle, but now let's put things in motion, right? S and L are quantities that are changing with respect to time. So what's the derivative with respect to time of both sides has to be equal, since both of these quantities are equal. So what's the derivative of S squared, first of all, with respect to time? Well, remember, S is a function of time, and it is with respect to time. So we have to use the chain rule. The outer function is S squared. The derivative of S squared is 2S times the derivative of the inner function being S. The derivative of S with respect to t is ds dt. What about the derivative of 2.25? Well, derivative of 2.25, that's a constant, 2.25, and therefore the derivative is 0. Okay, that distance there doesn't change. S and L, those distances do change. Similarly, on the right, then we have the derivative of L squared by the chain rule is 2L, derivative of the outer function, times dl dt, derivative of the inner function. Okay, so this is my related rates equation here. Notice I can solve for dl dt. First of all, notice I can divide both sides by 2, and then I can divide by L. So dl dt will be what? S divided by L over ds dt, or S ds dt divided by L. Oops, this should be, sorry, ds dt there. I've swapped sides, by the way, sorry. So dl dt is S divided by L ds dt. Okay. Or the way I'm going to write it up here, we'll see, is S times ds dt over L. Okay. So I can now find dl dt. When S is 3.7, I'll know what S is. I know ds dt from up here is 81 kilometers per hour. The question is, what is L? Well, we can find L at that instant. So when S is 3.7, remember this relationship holds at any point in time. So if I replace S with 3.7 here, I get 3.7 squared plus 1.5 squared is L squared. And so if I square 3.7 and square 1.5 and add them together, I get 15.94. So L would be the square root of that, 15.94. So dl dt then is S times ds dt. Remember ds dt, 81 kilometers per hour, divided by L, right? And L was the square root of 15.94. So if I use the calculator to do that, they do want this to be rounded to 3 decimal places. So be careful. You've got to go all the way out to do that. So when I use the calculator to calculate this, just to show you that, square root of 15.94, right? And so notice, because the 4th decimal place is an 8, right? We're going to round that 5 up to a 6. Notice the units, so 75.066, the units have to be kilometers per hour. We obviously, because our rate of change for the automobile, the speed that it's moving is that. So the rate of change of L with respect to time is 75.066 kilometers per hour. You can also get that from the fact that, right, S is in kilometers, L is in kilometers, so this is unitless. ds dt is in kilometers per hour, so we get that correct unit. Okay, so hopefully this makes sense. It's certainly reasonable. We know that L is lengthening, right? As this car moves this way, the distance from the house to the car is increasing, and so we would expect dl dt to be positive. Okay, I hope this is helpful.